Hi, Michael.
Hello.
Okay, we can wait a little while before the other students show up more. I see you have a lizard in your back, am I right?
Yeah, that's a lizard.
Is that your pet?
No, I caught it when I was in Florida, and then I put it in my pocket so I wouldn't lose it for a little bit. Then I let him go
Oh,
later.
oh, okay. That's kind of you. I don't know if you know that in the Buddhist religion, if you let go of a life, you bring brownie points to yourself. So if you travel in the Far East, you will see that people will purchase pets like turtles, tortoise, and then release them to nature to get brownie points.
I did not know that.
You did not know that? So you will know if you travel to Asia and see people doing that. So you have collected a brownie point for yourself.
Perfect.
Okay. So let's get started. We have 4 people here. Jiang Wan, David Alexander, Jen Liu, Joe, and Michael Williams. So let's get started then. Before we get started, do you have you guys did wow? Um, so so you should be happy. Okay. Since my default microphone has been changed, let me share my screen. So today we are going to talk about an interesting topic again. There's so many interesting topics in this course that I can go on, and I can share with you my knowledge in this field, and it will go on and on. But let me just share with you some of my knowledge on Summerfield integrals. So Summerfield integrals are important because it allows you to put a point source on top of a layered medium. So we will talk about spectral expansion of sources, point sources on top of a layered medium, and plus many of the other things. We are not able to complete everything here, but you will have a snippet of everything so that you can have a feeling as to what these things are. So this is Summerfield. I'm a big fan of Summerfield because you can see that he actually has contributed tremendously to science, actually the science of electromagnetic waves as well. He himself did not win the Nobel Prize, but many of his students did. I think if you look at this slide, he got some awards, but many of these students are awarded Nobel Prizes, 4 of them. Okay, I don't remember which 4 now. Okay, But anyhow, he's a remarkable gentleman. He actually solved this problem around 1909, and hence many of the integrals that you encounter in this knowledge is related to him or given his name. So we'll first by studying the spectral representation of a source. Okay. Let me see. I don't know how to use the keyboard. I was wanting to put a hyphen here, so I can type it in. Okay. Okay. So let's see what this is. The idea is that the idea we have learned in this course is that when you have a point source, the point source produces spherical waves. Okay, and these spherical waves can be described, for instance, in a very simpler case by e to the ikr over r. I'm going to use e to the minus I omega t time convention to replace the electrical engineering e to the j omega t time convention, because we are going to the part of the course which is closer to optics and physics. This is usually done in the optics community. This is usually done in the EE community. And if you're in microwave engineering, if you're in circuit theory, then you use either the j omega t time convention. And then you just have to switch around. But I hope you are capable of doing the switch. So this is a spherical wave that I have just written down. The problem with the spherical wave is that it's not commensurate with a planarly layered medium. So if you put a point source on top of a planarly layered medium, the spherical wave cannot be used to mesh boundary conditions very easily on top of a layered medium. So it has to be solved by other means. I like to point out the fact that this problem was attacked in 1909 by Summerfield. And the reason why he was interested in this problem was the problem of a radio wave. So if you have an antenna, and then you have a radio wave between the interface of the air and the earth, and if your observation point is over here, say, what do you see? What is the physics of the wave that you see? So this question was asked long ago, and Summerfield provided the solution then. So let's see how we can go about solving this problem. The first thing you need to do is to do the spectral expansion of a point source field, which is use Fourier integration technique to expand the point source field in terms of plane wave. Spectral here means Fourier transform expansion. So the first thing we need to do is, if we have these equations to solve, I'm going to use k instead of beta now. Okay, k and beta are interchangeable in optics and electrical engineering. And that if I want to solve this problem, which is essentially the Green's function problem, and I have a point source on the right-hand side, which is actually just this thing over here. Let me erase this. Okay, let me write down the word Earth here. Okay, and as I said before, we are going to switch over to K. Then we're going to Fourier transform this. That is that phi is Fourier transformable, and hence a Fourier transform representation exists, but it would be a 3D Fourier transform. So I have to write this thing in terms of 3D Fourier transform, and then I would have something like dkx, dky, dkz, phi tilde. I will call the Fourier transform this phi tilde. It would be in terms of kx, ky, and kz variables. Okay, and then I can write in terms of Fourier integrals, kxx plus ky, y plus kz, z. Okay, so can you see this? I have just used a 1D Fourier transform 3 times. If I were to have a 1D Fourier transform, I will have this simple relationship. I will have this rather simple relationship. But I'm using this simple relationship 3 times in order to get this expression out there. Okay, and in order for the 1D Fourier transform to exist, do you remember what the requirements are? When can I explain a function in terms of a Fourier transform? This is a question in signal processing. This question should be asked a lot in signal processing. Does anybody know? Okay, in order for a Fourier transform to exist, a function has to be absolutely integrable. And in 1D, it would be this one. Not square integrable, but absolutely integrable, which means that if you take the absolute value of the function and integrate from minus infinity to infinity, it has to be bounded. Okay, this means bounded. And if a function is absolutely integrable, then its Fourier transform exists. I'm not going to prove this. I'm sure that if you go home, you can prove this quite easily. Okay, so with this knowledge that I can write something in terms of a Fourier transform, then the Laplacian that I have in the previous equation over here, let me see, you can make this bigger, not any bigger. And then what I have is that this would be explicitly written as partial y squared plus partial z squared. And then I am going to use that to simplify this expression. Okay, I have this expression, but I will plug in the Fourier representation that I have from the previous slide. And what I have then is that I'm going to have this as 2 pi cubed, and then there will be this triple integrals. And then I would have dk cubed. I'm going to use the shorthand notation to write this cumbersome thing as just dk bar. Dk bar just means that it's dkx, dky, dkz. And then I'm going to bring this Laplacian inside. Okay, and then it will act on this part of the thing because this is the only part that depends on x, y, and z. And then I can still put back my phi tilde. And I'm going to use a shorthand notation for this very long thing in there. I will just use k bar. Okay, and then I'm going to use the shorthand notation for this. Essentially looks like a plane wave that we had before. Okay, so I'm going to use the shorthand notation and write the exponent as a k dot r. Okay, where k, of course, you remember from your plane wave course or plane wave lecture, this is just equal to this. And then your r for your plane wave lecture is xx plus yy plus zz. Okay, now if you remember that the Laplacian is equal to that, and this is the only part that depends on x, y, and z, then this Laplacian can be written. And if I were to take this to the next line, it'll be 1 over 2 pi cubed. and then decay bar. Decay bar here means dkx, dky, dkz. And then I have k0 squared minus kx squared minus ky squared minus kz squared. Okay, that's what happens to the Laplacian when it operates on this function. Okay, can everybody catch that? Okay, I hope you can catch that and it will not be too difficult for you to catch that. And now if we plug in the right-hand side, okay, the left-hand side has been expressed in terms of a Fourier transform integral. Okay, let me write this 2 properly. This should be a 2. Has been written in terms of a 3D Fourier transform integral. I would also like to write the right-hand side in terms of a Fourier transform integral, and we know what to do with that. And if we were to use the Fourier transform representation for delta function, you will have delta x, delta y, delta z on the right-hand side. And if you remember that, well, from your undergraduate course as to how to write a Fourier transform of a delta function integral is, then it will be just e to the ikxx plus ikyy plus ikzz, just this. Because we have learned previously that if you have just one delta function, its Fourier transform representation is given by this. Okay, if it's just one delta function, this would be its Fourier transform representation. But since we have 3 of them, its Fourier transform integration would be 3-dimensional. Okay, let me write this properly and so on. So I have expanded the left-hand side in terms of a Fourier transform integral, and also the right-hand side in terms of a Fourier transform integral. So two Fourier transform integrals are equal to each other if they are equal to each other for all space. In other words, if this thing, which is the left-hand side, equals this thing, which is the right-hand side, and if they're equal to each other for all x, y, and z, which means that is for all r, then essentially you can remove the Fourier transform integral. There should be a decay bar here, sorry. There should be a decay bar here. And I can essentially remove the Fourier transform integral and claim that the integrand must be the same. Okay, and you can also prove this quite easily by doing a Fourier inverse transform on these 2 expressions. Once you do a Fourier inverse transform on them, then the integral will disappear, and the integrand must be equal to each other. So now you can equate the 2 integrands. And if you equate the 2 integrands, you arrive at the fact that phi tilde, let me use a shorthand notation, is equal to minus 1 over k naught square minus kx square minus ky square minus kz square. Okay, this is my phi tilde. This is wonderful. I have a very simple expression for phi tilde, which means that I have another way of solving this problem in closed form. This problem has been solved in closed form before in your previous homeworks and lecture notes. It is essentially the Green's function of the system. We know what it is. But in order to write the solution in terms of plane waves, okay, you can see that these things look like plane waves. We have to use Fourier transform to find a different way of finding the solution. And then after that, we can say that, well, phi of r now, which is this expression over here, okay, phi of r, which is this expression over here, then can be written as being equal to, using this expression that I have in the previous slide again, that this thing has been found now, this has been found. So I can write this phi as being equal to 1 over 2 pi cubed. I believe I still have to put a minus sign out front. And then I will have to do a three-dimensional integral still. And I use the shorthand notation to write that thing in the exponential. And then phi tilde has been found. And it will be just k0 squared minus kx squared minus ky squared minus kz squared. Okay. So are you with me so far in finding this alternative solution to the Green's function problem? Essentially, we are trying to find an alternative way of solving this problem. And this is essentially the Green's function problem that we have solved many times over before. And we know that this should be equal to this. Okay, this should be equal to this. But this is wonderful. The left-hand side looks like plane waves. Okay, the right-hand side is spherical wave. We're almost there. We say that a spherical wave is not commensurate with the layered medium problem. So we like to find a plane wave expansion of this spherical wave. We are almost there. And in the sense that this is not truly a plane wave because it's a Fourier transform integral. So kx squared plus ky squared plus kz squared can be anything. So if you think about this Fourier transform integral, there's no restriction on what the sum of kx squared plus ky squared plus kz squared should be. And this could be anything. And that is not the nature of a plane wave. A plane wave is a wave where this has to be equal to k naught squared. Okay. And we have not this equality yet. Can you see that? This is a general Fourier transform integral where kx squared can be anything, ky can be anything, kz can be anything. So the sum of these three numbers can be anything, not k naught squared. If it's truly a plane wave, if you go back to your chapter or lecture on plane wave in a homogeneous medium, then this relationship has to be satisfied. This is called the dispersion relationship. In other words, the plane wave that we have on the left-hand side does not satisfy the dispersion relationship. Okay, and we have to do something to make the solution or the plane wave in this integrand satisfy the dispersion relationship. This is achieved by doing contour integration. And this part is just math. Okay, there's very little physics there, but just math. I would encourage you, if you cannot follow the math, you can go back and read again and see if you can follow the math. What I'm saying is that we have this triple integral on this equation over here. I'm going to write this triple integral explicitly in terms of three integrals. Okay, so I'm going to say that the spherical wave is going to be, let me write in terms of a double integral first, in terms of dkx, dky, and then I will take the variables that has something to do with kx and ky outside. Okay, this has nothing to do with kz, and I will do the kz integration last. Okay, and then I'll put the integrand back in, k0 squared, kx squared minus ky squared minus kz squared. So I focus my attention on this innermost integral. It only has one variable. It only has one variable. Then I can use what I have learned in my complex variable course before called the Cauchy integration technique. And if you have been studying signal processing, you might have come across this before. what you do then is to try to look for poles of the integrand. Okay, poles of the integrand. Since I'm doing the kz integration, I would look for where the poles are and try to use Cauchy's theorem to simplify my integration. So if I were to, let me see, do I have those pictures? Maybe I have some nice picture here. Okay, there's a nice picture here. Let me just put it above. So if I were to look at the integrand now, let me just do that. And if I look at the integrand now, and using this nice picture that I have, the pole location in a complex KZ plane, since I'm doing this KZ integration, I will look at the pole in a complex KZ plane. And you can easily show that pole at KZ equal to plus or minus K0 square minus KX square minus KY square, right? I think you can solve this in your head quite easily. When Kz equals this value, plus or minus, then the denominator will go to 0, indicating that a pole exists. So what do we do then? If the pole exists, then we can do Cauchy integration technique, which means that if I can do contour deformation, this is the Kz integration. Okay, this is the Kz integration. I can do contour integration technique and add a complex contour over here. And this has to have 0 contribution, okay? Contribution from C is 0. So if I add this contribution, which means that my original integration, my original DKZ integration is along the ray axis, and it doesn't hurt if I add something that is 0. I'm not going to go to the proof. You can actually prove by Jordan's lemma. There's something called Jordan's lemma. If you had a course in complex variable, you might have come across this before. And the integrand goes to 0 sufficiently fast enough that the contribution from this is 0. And then you argue that this integration is the same as this integration plus this integration. Okay, it's the same thing. And since I'm just adding a 0 integral to it. And then by Cauchy's theorem, this integration is equal to the integration of the integrand around the pole. Okay, that's where the pole is located. Okay, so this is pole. So I can pick up the residue of the pole by performing an integration just next to the pole singularity. And it's something you might have learned in complex variable theory, so I would not belabor the point. The important point is that this integral can be performed in closed form. Okay, it can be performed in closed form. And if this is for z equal to 0, okay, this is for z equal to 0. And then when z is less than 0, you can show that you can actually pick up this other pole. Okay, it will be described in the lecture notes. I wouldn't belabor this point again because this is mathematically tedious, but quite straightforward if you're good in mathematics. And for z less than 0, I pick up this singularity. And at the end of the day, the take-home message is that this integral can be written as just a 2D integral because one of the integrals has been performed in closed form. And finally left out with this, kxx plus kyy over, and you pick up a pole residue, and that turns out to be kz prime, and then you will have to multiply by kz prime z. Okay, where kz prime is not free anymore. Kz prime has to be such that it is equal to k0 square minus kx square minus ky square, which means that I have a new relationship now. If I perform the integral using Cauchy integration technique, I'll arrive at this two-dimensional integral. The two-dimensional integral has a new kz prime. You can easily see that this kz prime satisfies the dispersion relationship. Okay, this is the dispersion relationship for plane wave. And by mathematical technique, I have written and forced this wave to look like a plane wave. Now, physically, this is a plane wave, whereas previously it was not a plane wave. Okay, and that kz prime is equal to that. Okay, so what you see is that if kx squared plus ky squared, you're integrating over all possible values of kx and ky. If kx squared and ky squared are large enough, then kz prime can become imaginary and you will have an evanescent wave. However, if kx and ky are smaller than k naught squared, okay, the sum of these two terms are smaller than k naught squared, then this is a propagating plane wave. So it has a spectrum of propagating as well as evanescent wave. Okay, so important thing that you can go back and contemplate on. I don't have a lot of time to discuss the detail of the physics. So this integral will have propagating waves plus evanescent waves. Okay, and this identity is called the Weyl identity. And you can do some manipulation. I don't have time to go into that manipulation, which is that you can write this identity in two-dimensional fashion, and you can have a new identity which is written in terms of cylindrical coordinates. And then you will get this new identity, which is that in cylindrical waves, okay, this identity is now expressed in terms of cylindrical waves instead of plane wave. And this is called the Summerfield identity. And Summerfield derived this around 1909, and Weyl derived this around 1919. Okay, so Summerfield actually did a more difficult problem. And in order to derive the Summerfield identity, you essentially have to do a, I already talked about Weyl identity, which is this one over here. And then I like to mention that if you do the Summerfield identity, essentially you change the integration from Cartesian coordinates to cylindrical coordinate system. And then you will have to think about this integration path. This integration path is good because it goes from 0 to infinity, which is efficient if you were to do it numerically. So the integration path will look something like this. And if you convert this into a semi-infinite or infinite integration path, you get what is called a Summerfield integration path. I don't have time to talk into the details of the mathematical manipulation that needs to get there. Okay, but there are all these variations of different things. So the most important thing is that we are now able to expand a point source field, which was originally a spherical wave, in terms of plane wave or summations of plane waves. I call that the spectral expansion. Okay, we call that the spectral expansion. And then if we can break those plane waves further into TE and TM wave, then we know how to propagate them through this layered medium. We know even how to find the reflected waves. Okay. Similarly, just like the waveguide case, then we can actually identify, like in region 1, different kinds of field components. The E1Z must represent TM to Z waves. The H1Z must represent the TE to Z waves. Okay, so once you know how to decompose your electromagnetic field into TE and TM type, you know how to propagate them through this layered medium. It's something that we have done previously in the course. So how do we extract the TE and TM components of a point source field? So we get back to our dyadic Green's function again, which you actually did in your take-home exam. Okay, we show that once you use the dyadic Green's function technique, the electric field can be written as this, and then this is for Hertzian dipole pointing in the, okay, if I have J of R, a Hertzian dipole pointing in the alpha hat direction. Okay, if I have this Hertzian dipole whose pointing direction is alpha hat, you can easily show that the electric field is given by this. Okay, and then you learn from your take-home exam that essentially this E is just I omega mu the R prime G of R prime dot J of R prime. Okay, essentially that is that. And then you can also obtain your H field by using Maxwell's equation. It's given by curl of E divided by I omega mu. And then if you plug that in, we take the curl, the second term goes to 0. Many of you didn't understand this or did not use the advantage that curl of grad is always equal to 0. And many of you carry your manipulation through assuming that curl of grad is not equal to 0. That is a silly thing to do. So if you have this curl of E, this term disappears, you only pick up this first term. You can show that the magnetic field is actually curl of alpha IL e to the IKR over 4 pi R. Okay, so to find the Z component of this field, you just need to dot it with Z. And for simplicity, let's assume that we have a vertical electric dipole. Alpha hat is Z hat. Okay, alpha hat is Z hat for a VED. Okay, alpha hat is Z hat. Then you can actually look at the Z component of this now quite easily. Okay, if you look at the Z component, you can actually pick out the Z component of this because this is a Z component. It will contribute to a Z component on this, but I'm not going to go through the details. And if you plug in the Summerfield integral, you can show that EZ is something like this. Okay. And you have only one single integral or Summerfield integral. So numerically it's more expeditious. Let me see how I can get rid of this. Okay, K rho cube over K Z J0 K rho e to the I K Z Z. And this Z component will represent TM to Z waves. Okay, and we know how to propagate this plane wave. This is essentially a plane wave. And we know how to propagate this plane wave through the layered medium, and we have done that in the previous part of the course. And I'm not going to do that in detail with you. Okay, I assume that you know how to do that. It just becomes very technical. Okay, once you have something like this, you can keep track of the plane wave that leaves this point source, and then keep track of how they propagate through the medium. And then you can figure the details out. I have written out the details in the lecture notes, so I will not talk about them too much. But the next thing I'd like to talk about is actually the stationary phase method, okay, which is a very interesting method because the Summerfield integrals and the Weyl identities are just too complicated, okay, to get any physical insight. For instance, if I look at my Summerfield integral that I have obtained previously, It's very, very complicated. And then if I put in the reflection coefficient, it's even more complicated. So if you start to put in these reflected coefficients, then a typical Summerfield integral will look something like this. The field in region 1 would be a complicated integral from 0 to infinity, the k rho over k1z, j0, k rho, and then I lump everything that is very complicated into this function called f. Okay, and then there's a plane wave propagating in the z direction. Okay, so typical Summerfield integral looks something like this, where this f could be something very, very complicated. Okay, so this Summerfield integral does not offer much physical insight. And I'm going to use an approximation method called the stationary phase method to find an approximate solution to this integral, or an approximation of this integral. And this thing is too complicated for KIPS because I have Bessel functions, and I like to use the Weyl identity to write down the solution. And by the use of the Weyl identity, I can replace this part with plane waves. The only unfortunate part is that I have to deal with double integral. Okay, and then I will have this Bessel function becoming plane wave again. And then I will have k1z, and then I will have this f kx and ky. This would become a function of kx and ky. You remember k rho square is equal to kx squared plus ky squared. So this will be a function of kx and ky, and then I will have to put my k1z back there. Okay, so the method of stationary phase says that this integral is difficult to compute, but if x, y, and z are large, you find that if x is large, y is large, and z is also large, if you were to make a small change in kx or a small change in ky, the phase would vary rapidly. The phase would vary rapidly. And so if you were to compute this integration over the kx and ky plane, the computation is extremely laborious because what you have is that you have a rapidly oscillating integrand. From this thing and this thing, you gave rise to rapidly oscillating integrand. And it's extremely difficult to compute when x, y, and z are very large. But there is only one yardstick in electromagnetics. What does it mean when x, y, and z are very large? It means that they are very large compared to wavelengths. So this statement is the same as x over lambda, y over lambda, z over lambda becomes very large because we don't have any other yardsticks. The yardstick to measure distance is wavelength. So if your observation point is very far from the source compared to the wavelength, you are far away. You're in a far field region. So let's assume that this to be the case. Then as I said before, the integrand is going to be rapidly varying. Okay, so if I were to look at the integrand, it will look something like this. Like say if I look at the function like if I look at this function, let me see, if I call my g kx, ky, lambda. Lambda is a large parameter. And if I call this to be this function, e to the ikxx plus ikyy plus ikzz, Okay, then this function is going to be a rapidly varying function. Let me write my kx properly. Kx is going to be a rapidly varying function of kx, ky, kz, t. T can represent kx or ky. So if I were to plot this function as a function of kx or t, where t can be kx or ky, then this function will be rapidly varying. Okay, if you to change t by a little bit, the phase would change, which means that most of the contribution to this integral would come from the part where the phase is the least rapidly varying. So over this part, T naught is when the phase is least rapidly varying. Then you see that the integrand will look something like this. And you can see that the other parts of the integrand will be rapidly varying. The integration will cancel each other. The contribution to the integration will cancel each other, except for the contributions in the vicinity of the stationary phase point. This is called the stationary phase point. Okay, this is called the stationary phase point. Essentially, I'm writing this that this should be lambda ht kind of thing. Okay, so if I looked at this function h of t, which is the thing in the exponent, it is not rapidly varying. It actually varies slowly as a function of t. Only after you multiply by lambda, which can be x, y, and z, which is a big number, then the function becomes rapidly varying. And the contribution to this integration will come from the vicinity of this stationary phase point, where the integrand is least rapidly varying. So the idea of finding the approximation to such integral is to find where the stationary phase point is. Okay, so if I have such a function, and for instance, if I look at my E1z, then I can write it as, let me write it out in full first. Okay, it could be a Summerfield integral or Weyl integral. It would be this very, very complicated function multiplied by this exponential function, which can be rapidly varying when x, y, z are large. Okay, let me put in the k1z here. Okay, when x, y, z are large, this thing is rapidly varying. But I can look for the stationary phase point at which this would be least rapidly varying. And you can actually work out the stationary phase point. It's given out in the lecture note. And let me just write down the answer for you. The stationary phase point actually turns out to be very much related to x, y, and z. If you were to re-express this in terms of Cartesian coordinate, the stationary phase point is given by k1 sine theta cos phi. And then kys is given by k1 sine theta sine phi, where theta and phi are related to the x, y, and z coordinate in spherical coordinate. Is, in other words, r is given by r sine theta cosine phi, y is given by r sine theta sine phi. And then your z is given by r cosine theta. Okay, so if you were to express x, y, z in terms of spherical coordinate system, you find that the stationary phase points have a very nice formula given by this. And then what you do then is to evaluate this function. This is slowly varying. Okay, this is slow varying. And you express and approximate this about the stationary phase point. by the argument that all the contribution to the integrand will come from this stationary phase point, okay? And then there should be a K1Z somewhere around. There should be a 1 over K1Z around here. Okay? So what I'm left with in the integrand then is equal to e to the ikxx plus kyy plus ik1zz over k1z. And this part, I can use back the Weyl identity and say that it becomes like the spherical wave again. Okay, it becomes like a spherical wave again. So you can make this stationary phase point approximation and look at this Summerfield integrals and get some physics out of these integrations, okay? And I will let you read about the details in the lecture notes because I don't have time to talk about the gory details of this thing. Another thing that you should very much bear in mind is the concept of Riemann sheets and branch cards. And if you really want to understand this field, you actually have to understand Riemann sheets and branch cards. The reason why you need to understand Riemann sheets and branch cards because I can give you a very simple example. If you don't have this, these are very important for good bookkeeping. Okay, I can give you an example, and you will probably have to scratch your head as to what's wrong with this proof. I can say the I is the square root of -1, but it's also the same as +1 over -1. And then it's the same as square root of 1 over -1. And hence it's a square root of 1 over I. And then you get I squared. If you multiply again across, you get I squared is equal to 1. You get -1 equal to 1. So this is a puzzle. Okay, why is this the case? Well, I arrive at this because I have very sloppy bookkeeping. I didn't keep track of my square roots. Every time I take a square root, I should assume 2 possibilities. Okay, if I assume all those 2 possibilities, then I would not have this paradox or contradiction. You can read about this in the lecture notes. This is how important it is to have Riemann sheets and branch cards in order to solve this problem in the unambiguous fashion. I'll let you go, okay? I have a lot to tell you, but I don't have time to tell you all about them. Okay. Are there any questions before I let you go?
Professor?
Yes?
Since the semester is almost ending and the final exam is also approaching, could you please tell us a little bit about how the final exam will be conducted? Like, will it be a take-home exam or?
Yeah, I would give it as a take-home exam as well. Then what happens is that it will be like your take-home for exam 1, take-home 1, take-home 2, take-home 3, except that the topic I cover could be from the whole semester. And then I will give you 4 problems instead of 3 problems. Okay.
Okay, thank you.
So it will be very much like your other exams. You have to do it on your own, of course. And you have 4 problems to solve instead of 3. And
Okay,
it will cover the rest of the semester's topics as well. Okay?
Yes, thank you.
Okay, that's a good question. Any other questions? Okay, if not, then I'll let you go and thank you for coming.
Thank you, Professor.
Thank you.
Thank you for coming. It's always nice to see you all here.